We have seen how to implement data structures such as stacks, queues, and heaps using the built-in list type of Python. It turns out that one can go beyond the built-in types in Python and create our own data types. So we will look at this in more detail in this week's lectures. So let's revisit what we mean by a data structure. So a data structure is basically an organization of information whose behavior is defined through an interface. So an interface is nothing but the allowed set of operations. For instance, for a stack, the allowed set of operations are push and pop. And of course, we can also query whether a stack is empty or not. Likewise, for a queue, the only way we can modify a queue is to add something to the tail of the queue using the function addQ and remove the element at the head of the queue using the function removeQ. And for a max heap, for instance, we have the functions insert to add an element and delete max, which removes the largest element from the heap. Now, just because we implement a heap as a list, it doesn't mean that the functions that are defined for lists are actually legal for the heap. So if we have a heap H, which is implemented as a Python list, though the list will allow an append function, the append function on its own does not insert a value and maintain the heap property. So in general, a call such as h.append7 would not be legal. So we want to define new abstract data types in terms of the operations allowed. We don't want to look at the implementation and ask whether it's a list or not, because we don't want the implementation to determine what is allowed. We only want the actual operations that we define as the abstract interface to be permitted. So for instance, if we have a stack S and we push a value V, then the property of a stack guarantees that if we immediately apply pop, the value we get back is the last value pushed, and therefore we should get back V. In other words, if we execute this sequence, we first do s.push and then we do a pop, then the value that we pushed must be the value that we get back. So this is a way of abstractly defining the property of a stack and how push and pop interact without actually telling us anything about how the internal values are represented. In the same way, if we have an empty queue and we add to it two elements u and v, and then we remove the head of the queue, then we expect that we started with an empty queue and then we put in from this end a u and then we put in a v. Then the element that comes out should be the first element, namely u. In other words, assuming that this is empty, then if we add u and add v and then remove the head, we should get back the first element that we put in, namely u. So the important thing is that we would like to define the behavior of a data type without reference to the implementation. Now this can be very tedious because you have to make sure that you capture all the properties between functions, but this can be done, and this is technically how an abstract data type is defined. Now in our purposes, we will normally define it more informally, and we will make reference to the implementation, but we definitely do not want the implementation to determine how these functions work. In other words, we should be able to change one implementation to another one such that the functions behave the same way and the outside user has no idea which implementation is used. Now this is often the case when we need to optimize the implementation. We might come up with an inefficient implementation and then optimize it. For instance, we saw that for a priority queue, we could actually implement it as a sorted list. And then we could implement insert as an insert operation in a sorted list, which would take order n time. But delete max would just remove the head of the list. Now, this is not optimal because over a sequence of n inserts and deletes, this takes time order n squared. So if we replace the internal implementation from a sorted list to a heap, we get better behavior. But in terms of the actual values that the user sees as a sequence of inserts and delete max, the user doesn't see any difference between the sorted list implementation and the heap implementation. Perhaps there is a perception that one is faster than the other, but the actual correctness of the implementation should not be affected by how you choose to represent the data. So this is the essence of defining an abstract data type. So a good way to think of an abstract data type is as a black box which allows limited interaction. Imagine something like an ATM machine. So we have the data structure as a black box, And we have certain buttons which are the public interface. These are the functions that we are allowed to use. So in this picture, imagine this is a stack, and the buttons we are allowed to push are pop and push. Right? We are allowed to remove the top element from the stack. We are allowed to put an element into the stack. Now this requires us to also add and view things from the stack. So we also have a slot for input, which is shown as a kind of thing at the bottom here. Okay, we have a slot for input, and we have a way to receive information about the state of the stack. So we can imagine that we have some kind of a display. So this is typically how we would like to think of a data structure. We don't want to know what's inside the black box. We just want to specify that if we do a sequence of button pushes and we start supplying input through the input box, what do we expect to see in the display? So other than this, no other manipulation should be allowed. So we are not allowed to exploit what's inside the box in order to quickly get access, say, to the middle of a stack or the middle of a queue. Right? So we don't want such operations. We only want those operations which the externally visible interface, or the buttons in this case of the black box picture, allow us to use. So in a sense, this is already implemented when we use the built-in data types of Python. If we announce that the name L is of type list by setting L to the empty list, then immediately Python will allow us to use operations like append and extend on this list. But because it is of list type and not dictionary type, we won't be able to execute an operation such as keys, which is defined for dictionaries and not lists. Likewise, if we define D to be an empty dictionary, then we can use a function such as d.values to get the list of values currently stored. But we cannot manipulate D as a list. So we can't say d.append, it will give us an error. So Python uses the type information that it has about the value assigned to a name to determine what functions are legal, which is exactly what we are trying to do with these abstract data types. We're trying to say that the data type on its own should allow only certain limited types of access whose behavior is specified without telling us anything about the internal implementation. Remember, for instance, we saw that in a dictionary, even if we add a sequence of values in a particular order, we ask for the values after some time, they may not return in the same order because internally there is some optimization in order to make it fast to look up a value for a key. So we have no idea actually how a dictionary is implemented inside, but what we do know is that if we provide a key and that key is a valid key, we will get the value associated with that key. We don't ask how this is done, and we don't know whether from one version of Python to the next, the way in which this is implemented changes. So our question is that instead of using the built-in list for stacks, queues, and heaps and other data structures, can we also define a data type in which certain operations are permitted according to the type that we start with? So this is one of the main things which is associated with a style of programming called object-oriented programming. So in an object-oriented programming, we can provide data type definitions for new data types in which we do precisely what we have been talking about. We describe the public interface, that is the operations that are allowed on the data, and separately we provide an implementation which should be private. We will discuss later that in Python we don't actually have a full notion of privacy because of the nature of the language. But ideally the implementation should not be visible outside. Only the interface should allow the user to interact with the implemented data. And of course the implementation must be such that the functions that are visible to the user behave correctly. So here, for instance, if we add a heap, the public interface would say insert and delete max. The private implementation may be a sorted list or it may be a heap. And then we would then have to ensure that if we are using a sorted list, we implement delete max and insert in the correct way. And if we switch from that to a heap, the priority queue operations remain the same. So in the terminology of object-oriented programming, there are two important concepts: classes and objects. So a class is a template, very much like a function definition is a template. When we say def and define a function, the function doesn't execute. It just gives us a blueprint saying that this is what would happen if this function were called with a particular argument, and that argument will be substituted for the formal parameter in the function, and the code in the function will be executed to the corresponding value. In the same way, a class sets up a blueprint or a template for a data type. It tells us two things. It tells us what is the internal implementation, how is the data stored, and it gives us the functions that are used to implement the actual public interface. So how you manipulate the internal data in order to effect the operations that the public interface allows. And now once we have this template, we can construct many instances of it. So you have a blueprint for a stack, you can construct many independent stacks. Each independent stack has its own data. The stacks don't interfere with each other. Each of them has a copy of the function that you have defined associated with it. Right? So rather than, so the kind of the main difference from classical programming is, in classical programming you would have, for instance, a function like say push defined, and it will have two parameters, typically a stack and a value. So you have one function and then you provided the stack that you want to manipulate. On the other hand, now we have several stacks, S1, S2, S3, etc., which are created as instances of this class, and logically each of them has its own push function. Right? So there is a push associated with S1, there's a push associated with S2, there's a push associated with S3, and so on. And each of them is a copy of the same function derived from this template, but this implicitly attached to a single object. Right? So this is just a slight difference in perspective. Instead of having a function to which you pass the object that you want to manipulate, you have the object and you tell it what function to apply to itself. So let's look at a kind of example. This won't be a detailed example, it will just give you a flavor of what we're talking about. So here is a skeleton of a definition of a class heap. So now we, instead of using the built-in list, we want to define our own data type heap. So there are some function definitions. So these are these things, these def statements, and these correspond to definitions of the functions. And what we will see is that inside these definitions, we will have values which are stored in each copy of the heap. So just to get a little bit of an idea about how this would work, right? When we create an object of type heap, we call it like a function. So we say h is equal to heap L. So this implicitly says, give me an instance of the class heap with the initial value L passed to it. Now this calls this function init, which is why it's called init. So init is what is called a constructor. A constructor is a function that is called when the object is created and sets it up initially. In this particular case, our constructor is presumed to take an arbitrary list of values, say 14, 32, 15, and heapify it. Right? So somewhere inside the code of init, there will be a heapification operation, which we have not actually shown in this slide. So this is how you create objects. You first define a class. We will look at a concrete example soon. You define a class and then you call the class sort of like a function, and the name that is attached to this function call or this class call becomes a new object. Now, as we said, we have functions like insert and delete max defined for heaps, but it's like we have a separate copy of this function for each individual heap. So in this case, we have created a heap h. So we want to tell h, insert in yourself the value 17. So we write that as insert with respect to h. So h dot insert 17 as opposed to insert h 17, which would be the normal functional style of writing this. Right? We would normally pass it the heap and the value. Here instead we say, given the heap h, apply to the heap h the function insert with the argument 17. The next line says apply to the heap h in function insert with the value 28. And then, for instance, we can now ask h to return the maximum value by saying h dot delete max and store the return value in the name v. So what we would like to emphasize is that an abstract data type should be seen as a black box. Right? A black box has a public interface, the buttons that you can push to update and query the data type, to add things, delete things, and find out whether the data type is empty and so on. And inside we have a private implementation. This actually stores the data in some particular way to make the public functions work correctly. But the important thing is changing the private implementation should not affect how the functions behave in terms of input and output. they may behave differently in terms of efficiency. You might see that one version is faster than another, or one version is slower than another. But this is not the same as saying that the functions change, right? So we don't want the values to change. If we have a priority queue and we insert a set of values and then delete max, no matter how the priority queue is actually implemented internally, the delete max should give us the same value at the end. So we saw that Python supports object-oriented programming. We shall look at it in more detail in the next couple of lectures in this week's course. But the main concepts associated with this object-oriented programming are classes and objects. Classes are templates for data types, and objects are instances of these classes. They are the concrete data types which we use in our program.